All right, so we have talked about a few theorems regarding continuous functions, and some of those theorems have involved creating new continuous functions out of old ones, either by adding, subtracting, multiplying, dividing, so on and so forth. This next theorem involves yet another way to construct continuous functions out of old ones. It's just phrased a little bit differently. So what it says is that f is continuous if f is continuous at b, and if the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x is equal to f of b, or in other words, this. Now there's kind of a lot going on in this explanation up here, but essentially what this is saying is that if you have functions f and g that are continuous, then you can bring a limit. And if you're taking the composition of those functions, f of g of x, you can bring the limit in. Now, the reason we had to introduce this new value b is because we're assuming that g of x is continuous at a, and that the limit is equal to b, because the b is the thing that ends up the output of this is what gets plugged into the f function out here. So we had to kind of introduce another value to take the place of that limit. But especially if a function is continuous everywhere, then you don't even need to think of it in those terms. You can just think if these functions are both continuous, I can bring limits inside like that. Okay. So let's take a look at an example here. I want to try and take the limit as x approaches pi over 2 of a function that's actually a composition of functions. So this we need to take the limit. These functions have this continuity criteria met, and in particular, the innermost function is continuous at pi over 2. The cosine function is continuous everywhere, because it's defined everywhere. So I could bring that limit in, and then in further to that cosine of x. I'm going to get sine of tangent of the limit as x approaches pi over 2 of cosine of x. Okay? So basically what that theorem says is unless we run into a domain issue or a continuity issue with this innermost function, we can bring that limit all the way into that innermost function. Okay, and you might look at this and think, well, tangent's not defined at pi over 2, but that's not a problem because we're not taking tangent of pi over 2. The limit's not being applied to the tangent. It's being applied to the function where the x is, which is cosine. Now, what is the limit as x approaches pi over 2 of cosine of x? Well, because cosine of x is continuous at pi over 2, I can simply plug pi over 2 in and use that. This is going to give me sine of tangent. What is the limit, or what is cosine of pi over 2? Well, it's equal to 0. Okay? Now, notice I've evaluated the only limit in the problem, and even though I'm not done, there are no more limits. Now it's just evaluating trigonometric functions. Tangent of 0 is equal to 0. So now we're looking at sine of 0, which equals 0. Okay? But that's basically what that theorem allows me to do. Bring the limit all the way in, evaluate the limit, and then, continue evaluating the rest of the function as we did here. Okay? That motivates this next theorem, which says that if g is continuous at a and if f is continuous at g of a, then the composite function f of g of x is also continuous at a. So this is basically giving us one more way of constructing continuous functions out of other functions that we happen to know are continuous. Okay, so here's another example kind of similar to what we did before. We want to determine where f of x equals the natural log of 5 plus 4x minus x squared is continuous. And notice what we have here is a composite of two functions, a logarithm on the outside and a polynomial on the inside. We already know that both of these functions are continuous everywhere on their domains, and so according to this previous theorem, if we want to determine where this composite function is continuous, it basically boils down to just determining where it's defined. So what I know about the natural log function is that its domain is all positive numbers, which means I need this quadratic function in here to only be positive. How do we determine where that happens? Well, you've dealt with this before. You would have dealt with this in pre-calculus or a college algebra class, quadratic inequality. I want to set 5 plus 4x minus x squared. I want it to be greater than 0. Okay? Now I like to have my x squared term first, but I notice that it's negative. So what I'm going to do is multiply both sides of this inequality by a -1, which will make that a positive x squared, and these two terms will become negative, and then I'll rearrange my terms. X squared minus 4x minus 5. And because I multiplied by a negative, my inequality flips around on me like that. Okay? I can factor this left-hand side, which is going to give me x minus 4, x plus 1 less than 0. And the way I like to deal with these quadratic inequalities is I like to create a number line, and I plot the zeros of this quadratic over here. So that's going to be -1, -1, and 4. That splits my number line into 3 intervals, and then you can pick test points in these intervals. So for example, if I picked -10, which would lie in this interval, plug it into my x's, do I get something that's negative, which is what we want, because we want this to be less than 0, or do I get something positive? Well, -10 minus 4 is a negative number. -10 plus 1 is -9, also a negative number. I have a negative times a negative, which is positive. We don't want that interval. What about here? Between -1 and 4 is the number 0. If I plug zeros in for my x's, I get -4 times +1. Negative times positive is negative, which is what we want. What about something over here? I'll plug in 1,000,000. 1,000,000 minus 4 is definitely positive. 1,000,000 plus 1 is also definitely positive. Positive times positive is positive, and we don't want positive, we want negative. At -1 and at 4, both of those would give me 0 on this side, and 0 is not less than itself, so I can't use these endpoints. We're looking at this interval right here, which is the open interval from -1 to 4. That is the interval on which this function is defined, and by the theorems that we've already talked about, it would then be the interval on which this function is continuous. Okay? We're going to end our section on continuity talking about a really important theorem called the intermediate value theorem. Now this theorem is actually not that difficult to understand intuitively why it's true once you understand what it's saying, but to mathematically prove it requires stuff that go well beyond this course. So interestingly enough, the theorem itself is not that difficult to understand, and it's not that difficult to believe is true. There's a very good intuitive argument for why it's true, but a formal proof of it requires much more advanced math than we cover in any of the calculus classes that we teach. So, intermediate value theorem. Suppose that f is continuous on the closed interval a, b. So here, graphically, I can see this closed interval a, b. And let's let n be any number between f of a and f of b. So again, notice if this is my curve representing f, a and b are here, then f of a would be here on my y-axis, f of b would be here on my y-axis as well, and n is just some number in between those, okay? And we're also going to be assuming that f of a is not equal to f of b. If f of a and f of b were equal to each other, then there would be no space between them to put that n there. Okay, so now that we've kind of discussed those conditions, if that's all true, then there exists some number c in the open interval a, b, so some number c between a and b, but not equal to either of them, such that f of c equals n. Okay, now when you read the theorem like this, it's really hard to wrap your mind around what's going on, but basically what it says is that if I have a function that I know is continuous on this interval a, b, those endpoints determine endpoints of another interval on my y-axis. And basically what this is saying is if I draw a horizontal line from any number at all between f of a and f of b, I will eventually hit my curve. That's basically what this is saying. And what it means to hit the curve is this horizontal line will intersect a point on that curve, which will correspond to some value between a and b. And if I plug that value in, it's going to take me to that number n. Now, what this theorem does not say is that it does not say that there's only one value of c that will do this. In some cases, there might be more than one. So for example, same function, if I choose n a little bit lower, if I choose my n here, then if I draw a horizontal line, I'll see more than one place where it intersects the curve, at least the part of the curve between A and B. So there's multiple values of C that would satisfy this thing that we call the intermediate value theorem on this particular, for this choice of n. But we can see here that there's not always more than one. The intermediate value theorem guarantees that there will be at least one value C that satisfies this, okay? Now, the reason this is intuitively true is because if you were to pick an A and a B and kind of decide ahead of time where f of A and f of B are, to draw a continuous function from A f of A to B f of B, you have to be able to do it without picking up your pencil. And there's no way to get from here to here, regardless of what this curve looks like, that will jump over any horizontal line that I could draw here. Okay, because if that were the case, then that would mean we have a discontinuity, specifically a jump discontinuity. But we're assuming that our function is continuous. So that means we're going to hit all of the y values that exist between f of A and f of B as we get from here to here. And that intuitively is why the intermediate value theorem, or I'm going to call it the IVT for short, that's intuitively why it's true. But that's not enough of an argument to make a nice formal mathematical proof. We're just going to accept that it's true. This should say IVT. I wrote IVP here. Sometimes we call a function that has the result of the intermediate value theorem. We say that it has an intermediate value property, which is sometimes denoted IVP. So I was thinking of the wrong thing there, but IVT is a good abbreviation to use. I have to change that one too. Okay, so the intermediate value theorem actually has a lot of different applications. I'm going to talk about two of them here. So the first one says we want to use the IVT to show that this equation has at least one solution in the intervals 0 to 2. Now, if you look at this equation, this is not one that you can solve algebraically. If it were just a polynomial equation, we could deal with that. If it were just a trigonometric equation, we could probably deal with that too. But if you notice, it's an equation involving a trigonometric function and a quadratic function. And I guarantee you, you're not forgetting anything from algebra if you look at that and think, I don't know how to solve that. You can't, okay? Now, it doesn't mean that there aren't other ways to find a solution, but anything you would have done up until this point are not going to get you that solution. But notice we're not actually trying to find an explicit solution. All we're trying to do is to show that a solution exists, specifically between 1 and 2. And I want to point something out here. This intermediate value theorem, is one of a few types of theorems that we encounter in calculus called an existence theorem. There's actually 4 existence theorems that we talk about in this class. The intermediate value theorem is the first one. The other 3 we're not going to see until chapter 4. Those are the extreme value theorem, Rolle's theorem, and the mean value theorem. And what I mean by an existence theorem is that it's a theorem that guarantees the existence of something without telling you how to find it. So notice here, it says, then there exists a number C. The theorem offers no guidance in how to locate that number C. It just guarantees that it exists. That's why we get the name existence theorem out of that. In this example, we're trying to show that there exists a solution to this equation without finding it explicitly. And how are we supposed to do that? Well, the trick is to start by subtracting all of this stuff over to the left-hand side. So if I were to do this, sine of x plus x minus x squared equals 0. Notice I just moved everything over to the side. Okay, then solving this equation is the same thing as finding the zeros of this function. So I'm going to define f of x to equal this function that I'm seeing on the left-hand side, sine of x plus x minus x squared. Okay, So now what I want to do is look at the interval that we're interested in, the interval from 1 to 2. And I'm actually going to plug those endpoints, 1 and 2, directly into this function. Okay? What is f of 1? You need a calculator for that. But if you were to plug it into a calculator, you're going to get something that's approximately 0.841. What happens if I plug 2 into that? Again, use a calculator. You're not going to be able to do that by hand. I would get negative 1.091. The relevance of these numbers is not the numbers themselves. It's the fact that one of them is positive while the other one is negative. Why does that matter? Well, suppose I wanted to graph these points. Remember, these would be points on the curve given for this function, or the curve of this function. The f of 1 is giving me a positive number, something like 0.841. So I would have a point there on my curve. F of 2 is giving me a negative number, negative 1.091 after rounding. That gives me a number down here. Okay. Now look at the function. Sine of x is a continuous function. It's continuous everywhere, right? Because it's trigonometric and it's defined everywhere. X minus x squared is a quadratic function. It's a polynomial. We know that those are continuous everywhere. And so according to those theorems that we've talked about, the sum of those two functions is guaranteed to be continuous everywhere. F of x is a continuous function. And notice continuity is one of the conditions that shows up in the intermediate value theorem. Now, if this is a continuous function, then according to the intermediate value theorem, if I pick any value, any number, n down here, or if I pick n over here or up here, anywhere, I should be able to find a number between 1 and 2, which the intermediate value theorem is calling c, such that f of c equals n. Well, notice that between these two numbers is the number 0. The intermediate value theorem guarantees that I can find some number c such that f of c equals 0. But that's exactly what we were looking for, because if such a c exists, then it would solve that equation. And to see why that's the case, you can just draw a picture. There's no way to get from this point to this point without lifting my pen that does not take me through the x-axis. Now, I don't know if the way that I drew that curve is accurate or not, because I'm only working with 2 points. In fact, this graph is, if you graph it in a graphing utility or a graphing calculator, looks very, very close to an upside down parabola. But I can see intuitively that I have to pass through my x-axis. There has to be some value c such that f of c is 0. Okay, but the intermediate value theorem is the mathematical justification for that. So I would say something like this. Because f of x is continuous on the interval 1, 2, it's technically continuous everywhere, but the statement of the intermediate value theorem references a closed interval. So even though it is continuous everywhere, more specifically, in this case, we could just say it's continuous on that interval. And because f of 1 and f of 2 have different signs, meaning one is positive and one is negative, then by the IVT, there must exist a number c in the interval 1, 2, such that f of c equals 0. Okay? And that would solve this equation. Okay, I actually have one more example that I want to do, but I'm realizing this example is going to take a little bit more time, and this is about as long as I want to make this video. So I'm just going to make one last video just for this example, and then that's what's going to wrap up section 2.5.